Good day, class. My name is Mr. Brown, and today we'll be discussing the topic basic logic gates and their truth tables. After this class, you should be able to define what a logic gate is, understand what a Boolean function is, identify the logic gate Boolean functions and or not NAND, identify the symbol for each logic function, and perform Boolean algebra between unknowns such as A and B. Create truth tables using a binary system and have an understanding of the visual representation of the switching function of a two-input logic gate for each logic function, as well as understanding the visual representation of the output for each logic function. Logic gates are building blocks for digital electronics. They perform basic logical functions, which are fundamental to logic circuits. And because of this, logic gates are used extensively in digital electronic circuits. Digital electronic circuits operate using high and low signals. These signals can be found in most of the systems we use daily. These systems include burglar and fire alarm systems. The three most basic gates are the OR gate, AND gate, NOT gate. The OR gate has two inputs and one output. The OR gate is shaped like an arrowhead, and the OR gate adds its inputs. Now, we're talking about digital electronics. Digital electronics use high and low signals. So generally, a high signal is equated to a logic 1, and a low signal is equated to a logic 0. You can only have two possible outcomes and two possible inputs, a high or a low. If you add 0 and 1, you get 1 in digital electronics and in maths. Now if you add 1 and 1, or a high plus a high, you get a high. So it's still 1. You may be wondering, that doesn't make sense. Well, it's easier for you to remember that that 1 is depicting a high. So a high plus a high is still a high. It can't be a low, and there are only two possibilities, a high or a low. So it has to be a high. The basic AND gate has two inputs and one output. The AND gate looks like the letter D, and the AND gate multiplies its input to give an output. The NOT gate has one input and one output. It looks like a triangle. The NOT gate inverts its input signal. This means if its input signal was high, its output signal will be low. And if its output signal was low, then its input signal will be high. Digital electronic gates can further be described using analog circuits. The simplest analog circuit comprises a switch, a power source, and a load or a resistor. A lamp, an incandescent lamp, is simply a resistor that glows due to the current that is passing through it. This occurs when the switch is closed, hence the circuit is complete. The AND gate is similar to a circuit that has two switches, S0 and S1 in series. Let's say that the state of the switches when they're closed and open are true and false respectively. Let us also say that when the lamp is lit, the output is true, and when the lamp is off, the output is false. When S1 and S0 are both open or false, of course the output will be false. When S0 is true and S1 is false, the output will be false. When S0 is false and S1 is true, the output will still be false. When S0 is true and S1 is true, only then will the output be true. What you just looked at, what we just created, is called a truth table, and it describes how the AND gate operates. Now, what if instead of having these two switches in series with each other, they were actually in parallel with each other? When S0 and S1 are both false, the output will be false. When S0 is true and S1 is false, the output will be true. When S0 is false and S1 is true, the output again will be true. When S0 and S1 are both true, the output will be true once more. What we just created is the truth table for the OR gate and describes how the OR gate operates. Now the NOT gate inverts its input signal. As we said before, this means that if its input signal was high or true, its output signal will be low or false. Of course, the converse is true. If its input signal was low or false, its output signal will be high. It's kind of like that annoying little brother. Let's say that you are at home and you're doing your work and your light is on, you're studying in your room, and he sees you and he laughs, ha 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 ha, turns off the light, runs away. Or if you're sleeping and your light is off and he passes and he sees that you're sleeping and he laughs, ha 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 ha, and turns on the light. Yeah, that's your inverter, your annoying little brother. The NAND gate is simply an AND gate whose output is connected to a NOT gate. So in essence, the NAND gate's truth table is simply an inversion of the AND gate's truth table. Now let's talk about the term called Boolean Algebra. You may be asking, what in the world is that? Well, by now we should all be familiar with the word or the term algebra. So let's start there. Algebra is a part of mathematics where numbers are represented by letters. So of course we use these numbers to represent, or rather we use these letters to represent numbers because we do not know what the actual numbers are. Your circuit will have ones and zeros going in and out. And if it is that these numbers are changing, then we have to use letters to depict the numbers because we do not know what those numbers will be at any specific time. George Boole investigated the mathematics we use to manipulate digital logic gates and circuits, and he called this branch of mathematics Boolean Algebra. Now, what happens if we actually join these gates together? Here we have an example. The first OR gate has logics 0, 1 at its input, which produces logic 1 at its output. The first AND gate has logics 1, 0 at its input, which produces logic 0 at its output. The NOT gate has logic 1 at its input. Obviously, we're going to invert, so it produces logic 0 at its output. The second OR gate has logics 0, 1 at its inputs, which produce logic 1 at its output. Let us go on to Boolean algebra in its purest form. The first OR gate has logics A, B at its input and produce logic A plus B at its output. The AND gate has logics A plus B, C at its input, which produce open bracket A plus B, close bracket times C at its output. The NOT gate has logic D at its input, which produces D prime or D bar at its output. Well, most persons will have used a washing machine or would have had their clothes washed in a washing machine in the past. The control circuit can be modeled as a combinational logic circuit, this combinational logic circuit comprises 4 AND gates, 2 NOT gates. The control system has 3 inputs: the door, water level, and temperature sensors, and 3 outputs: the water valve, heater, and motor. The water valve, in this case, will be on when the machine door is closed and the water is below its required level. The heater will be on when the machine door is closed, the water is below the required level, and its temperature needs adjusting. For the motor to start, the machine door must be closed and the water at its required level and temperature. So let's do a recap. Logic gates are building blocks of digital circuits, and they perform the basic functions which are fundamental to these digital circuits. Digital electronic circuits operate using high and low signals, ones and zeros only. Only two possibilities: a high or a low, a 1 or a 0, true or false. Two possibilities only. The AND gate multiplies its input signals. The OR gate adds its input signals together. The NOT gate inverts its input signal, and the NAND gate is basically an AND gate with a NOT gate at its output. Now, look around you and tell me what appliances you're seeing and whether or not you think that digital electronics is used in their operation.